Now, let's quickly go through one example problem, and you can see here we are dealing with the same I section that what we used in the previous module, which is a 1 meter height beam, I section beam with a flange width of 500 mm, flange thickness of 200 mm, and then web thickness of 150 mm, and you have pre-stressing strand of 10 numbers of half-inch diameter strand. And what we are interested in calculating is, this is the initial stress. Okay, you can see the average pre-stress after short-term loss is 0.71 FPK. So you see, usually we said FPI is 0.75 FPK. So what they are saying is, after the short-term loss, what the stress left is 0.7. That means 0.04 FPK is lost because of the short-term loss, right? And the age of loading, so you start loading it at the age of 28 days, which is good, right? After significant curing, if you start loading, your creep and shrinkage effects will be less. And curing here was done for 7 days, and elastic modulus of pre-stressing steel is 2 × 10⁵ megapascal, and elastic modulus of concrete is given as 35,000 megapascal, grade of concrete is given as 50 megapascal. Now we need to calculate what are the loss of pre-stress due to creep, shrinkage and relaxation at the end of 5 years. And we can neglect the weight of the beam in the calculations, and relative humidity is taken as 70%. So let us see now how do we calculate each of the loss that is happening from relaxation, creep and shrinkage. And these are the cross section properties. I think it is the same cross section that we used previously. Gross sectional area is 290,000 millimeter square. Gross moment of inertia is 3.536 into 10⁻⁻10, and the central axis is a symmetrical cross section. So centroid is right at the center, which is 500 mm from the bottom of the beam. Okay, and we got these numbers, and area of pre-stressing steel is given as 10 into 10 numbers of half-inch strand. You know, half-inch strand, each one of them is about 99.7 millimeter square. So the total area of pre-stressing steel is 997, and pre-stressing force after short-term loss P0. That's why here we are writing that as P0. Okay, so P0 means the force after the short-term loss, which is AP into FP0, 997 multiplied by 1320. Now how do we get the 1320? Which is 0.71 FPK that is given in the problem. So you have a force of 1316 kilonewton. Now let us look at, this is again the cross section. We are trying to calculate again the stress at the level of steel, right. So let us calculate. Now you have, this is your CG and this is your eccentricity. Now what is eccentricity here? Eccentricity is 400 millimeter, right. So you have two components. You have a normal component that is happening from P0 by A. Again at this level I am going to have compression because pre-stressing is at the bottom, pre-stressing steel is at the bottom, it is going to be compression. Then there will be a moment due to pre-stress, moment is P0 into E, moment is P0 into E. Now we are calculating the stress at the level of steel. So now what is this again? YB, YB will be nothing but E only, right. So this both of them will be same. So YB is again 400, so P0 is 1360 and into E is 400, I is 3.536 when you substitute, and YB is 400. When you substitute all this magnitude, you get the stress of negative 10.49 megapascal, which is compression, because we have taken compression as negative, right. So you get these values. Now let us look at now to calculate your creep loss. First we need to calculate the creep coefficient phi naught, that is given in 6.251 in the IS 1343. Now let us look at it. Now we have RH value that is given as 70%, but the code is giving you table. This is a simplified quick calculation that what we are doing for 50% and 80%. So for 70% you need to do the interpolation. So let us see now how do we do the interpolation. Again, if you look at it, the age of loading is 28 days, right. So we need to use this 28-day values and then interpolate depending upon the notional size coefficient what we have, and the RH of 70%. So let's look at it. T naught is 28 days, cross section area is 290,000 millimeter square, relative humidity is 70%. The exposed perimeter is, now this is an I section. So you have to calculate what are the surfaces that are getting exposed, right? So you get 2 into 200 plus 2 into 175 plus 2 into 600 plus 2 into 175, 200 plus 500. So we do that. Typically for a girder, you will have a deck slab or slab will come. So the top surface in the cross section will not be exposed. So all other surface that is exposed is being used for calculating the perimeter. So you end up with perimeter of 3200 millimeter. Now cross section area we know 290,000 millimeter square. So I can calculate my notional size coefficient as 181.25 millimeter, right. So now we have values for 50%, again 181. So I have to interpolate between 150 and 600 for both the tables, and then I have to do double interpolation. So when you do the double interpolation, you get the final creep coefficient as 2.046. Again, this is the maximum value that happens at 70 years. Now we are not doing calculation for 70 years, but we are doing calculation for lesser time. So we need to apply some reduction factor as well. So let's see how do we apply the reduction factors, right? Now, so this is from table. Now we can also do this calculation from 6.251 as well. So this is a more accurate, let's say, calculations. Let's see now how do we get. This is first, this is using a table we got the phi naught. Now next one is from equations also we can calculate. This will be much more accurate. So we can say what is phi RH, which is nothing but again reduction factor accounting for the relative humidity. So we have calculated H naught, and this RH is 70%, 70, and we don't know what is alpha 1 and alpha 2, that needs to be calculated. And alpha 1 and alpha 2 are again empirical equation that are given in your IS 1343, and it is directly a function of your grade of concrete. So grade of concrete is 50, so substitute and you get alpha 1 of 0.837 and you get alpha 2 of 0.95, and then when you substitute that, the reduction coefficient for humidity effect works out to be 1.371. Okay. So we got only this factor. Now again we have to calculate strength factor and then the T naught factor as well. So let's look at now how to get your strength factor. Again the equations that are given in IS 1343. So you substitute FCK value and you get your beta FCM as 2.206, and T naught is, we have seen that age of loading is 28 days. So you put 28 days and then you get the value of 0.488. Then finally when you substitute all the factors, you get a coefficient of 1.476, which is much lesser than what you got from the table, because same table interpolation is a very simple way of quick calculation for your phi naught. But if you want to have more accurate calculation, you have to use these equations, and this way you get your phi naught of 1.476. And you see from the table we got 2.046, which is a conservative one, okay, which is a conservative one, but this is much less than 2.046, right. So you will get less loss if you use the equations than the table. Now now that we have calculated all these coefficients, and this is the phi naught that we have done. Again, one from table, one from equations. Whatever the way that you do it, this is the value that happens at 70 years. Now what we are interested is in calculating at 5 years, at the end of 5 years. So we need to apply some reduction factor, which is again a function of some reduction factor that depends upon T naught, the age of loading. Then we have to calculate this beta factor using this equation, and this equation also has time t. Now you can see that time t is going to be for 5 years, which is in days it's going to be 5 into 365, that we need to put t equal to 5 into 365, and beta h is the reduction factor for humidity. Again an equation is there, here you put 70 and then here you put 100 and then you get your value, and then we also need to calculate our alpha 3 value, and this equation is valid for when FCK is more than 45 megapascal, and there is one more equation is available when FCK is less than 40 megapascal. So, you calculate all these factors and then you plug in and you get your beta H factor as 503, which is less than 1500, and then you put here 503 and then you get your reduction factor, because again 1825, this is 5 into 365, T naught is 28 days, that is already given, and beta H we calculated to be 503.91. So, when you plug in all these equations, there is a reduction factor of 0.925. That means you can see I'm taking a phi naught value that is that will happen at 70 years. But what you can see is even at the end of 5 years, almost it has reached 92.5% of what value that will happen at 70 years. That means the long term losses are happening more quickly at the initial stages than at the later stages, right. So, in this way, if you get this exact phi value, it works out to be 1.365. Now that we got your creep coefficient, now the loss in pre-stress due to creep, we know that it is elastic modulus multiplied by the creep ultimate strain, but creep ultimate strain can be calculated from phi into epsilon elastic. Now, phi we have calculated. Now, what is epsilon elastic? Epsilon elastic is the strain in the concrete at the level of this pre-stressing steel. Now, strain can be calculated by stress by elastic modulus. Stress we have already calculated to be 10.492 megapascal. So, if you plug in this value, it is nothing but modular ratio multiplied by creep coefficient multiplied by stress in the concrete at the level of steel. So, when you plug in all these equations, you get 81.77 megapascal, which is the loss in pre-stress that is happening because of concrete creep at the end of 5 years. Now, what would be the creep loss at the end of 70 years? There is no reduction factor. You go back and use 1.476, it will be 5.71 multiplied by 1.476 multiplied by 10.4. It will be higher, slightly higher, right. So, in this way, you can calculate the loss in pre-stress due to creep of concrete. Now, let us see how do we do the calculation for loss of pre-stress due to shrinkage. And shrinkage strain calculations, as we have explained, it is given in 6.252 of IS 1343, and we have two strains, epsilon CD and epsilon CA, and for epsilon CA is an autogeneous shrinkage strain. For M50, we know the maximum value, this is a maximum value, again we take that as 75 microstrain, and we need to apply some reduction factor, because we are not doing the calculation at 70 years, we are doing the calculation at 5 years. So, this is a reduction factor, which is a exponential function. T is usually taken in this equation is in days. So, you substitute that and you get a reduction factor of 0.9. It is almost close to that of 1. That means at the end of 5 years, pretty much whatever the code value that is given in the table will happen, right. So, that is what it is. So, in fact, the shrinkage also happens very fast in the initial time and then it plateaus. So, if you are calculating at 5 years or 2 years, pretty much this value will be reached. Okay, now let us do the same exercise for drying shrinkage strain. For drying shrinkage strain, again we are calculating, given that relative humidity is 70%, the code gives you the maximum value of 300 into 10 to the power minus 6. So, basically for 50 you have to do the interpolation and then you get 300 for RH equal to 70%, okay. So, for 50. So, that is how we get this 300 into 10 to the power minus 6, and then again we have to apply some reduction factor, because these are the value that will happen at 70 years, but we are calculating at 5 years, and you will find that it will be very close. So, let's check what are the reduction factors we get. We got epsilon CD as 300 microstrain. Now, I need to calculate the reduction factors KH and beta DS. Now, let us see what is beta ds, again function of your notional size coefficient, and Ts is the time of curing. Now, larger the time of curing, again the beta ds will become less. So, less means I have to take only lesser strain for calculations. And KH factor also, I think previously we have calculated, that works out to be 0.878. So, when you substitute all these values, you get your drying shrinkage strain as, instead of 300, you get about 250. So, you can see that even at the end of 5 years, you are pretty much getting close to that of 300. There is only small 50 microstrain less, right. So, you get 250 microstrain. Now, we got both the strains. Again, this is the total strain that is lost. So, that much shrinkage will reduce the stretching in the strand, right. So, EP into this strain will give me the loss in pre-stress, which works out to be 65 megapascal, right. So, in this way we have calculated that. Now, we have done creep, we have done shrinkage. Now, let us look at what are the relaxation loss due to pre-stressing. Now, the values are given in table 6, as you can see, for initial stress 0.71 FP that we have said, for 1825 days, you can see that the code value gives us 5.3%, and why we are multiplying this by 3? You see the code, the table value that what you have discussed is valid only for 1000 hours. Now, we are doing it for 5 into 365 into 24. So, which is much larger than 1000 hours. So, that is the reason the suggested value has to be multiplied by a factor of 3. That is what the code says. So, when you do that, the relaxation loss is 15.9%, or we can go ahead and use the equation that we discussed, which was developed by Magura in 1964, and T is given in hours, and FPI is the initial stress, FPY is the yield stress. So, if you plug in this equation, again you will get your actual stress in the loss. Okay. So, if you substitute again, you know, here we are assuming that we are using a stress relief stand. If you are using a low relaxation stand, this value will become 45, that we have discussed it in the previous slide, right. So, if you plug in this equation, usually we take FPY to be 0.9 FPU, and FPU you know is equal to 1860 megapascal, and so you can plug in this value and you get the stress is 1175 megapascal. So, you see here 1320 was the initial stress, it has become 1175. So, that means 145 megapascal of stress is being lost because of relaxation at the end of 5 years. So, but the code values for previous slide, if you go, that works out to be, you can see it is only 15.9%, which is on the higher side, but using this equation you will end up with a lower value. So, always when you are doing it more than 1000 hours, I strongly recommend you to use the equation, and then that will give you the more accurate representation of your relaxation loss. So, now that we have done these loss, so we have calculated loss because of the relaxation, we have calculated the loss in pre-stress due to creep, we have also calculated the loss that is happening from shrinkage. Now, let us look at in terms of forces what is happening. Now, due to creep we said 81.77 megapascal is lost, right. So, that multiplied by area will give me the force. So, due to creep I have lost about 81.52 kilonewton of pre-stressing force. Due to shrinkage, again it is also not quite less. So, 65 megapascal multiplied by 997, I have lost about 65 kilonewton. And if you look at relaxation, in fact, in this case, the relaxation is seeming to be much higher, right. So, it works out to be 145 megapascal multiplied by 997, you see 144.56 kilo. So, when you add all of them, you see here 81.52, 64.42, 144.56. So, you are losing almost to 291 kilonewton, which is not a small number. Okay. So, especially when you consider the initial stress as 1316, and if you take the ratio, we are losing almost 22% of initial stress is being lost because of the long term effects. So, that is the reason, especially for old structures, when you do the calculations properly, we need to estimate these losses in a proper way, because the long term losses can be quite significant. over a period of time. So that is the reason, in fact, most of the time design engineers are not aware. They always calculate only short-term deflections. But the deflections also will keep on increasing because of the shrinkage and creep effect, which we need to account for it, particularly for longer members, and usually pre-stress systems are longer. So you go for pre-stressing only when you have a longer member. So we need to account for these long-term losses in a more rational way. Okay. So let's summarize whatever we have discussed. So we have discussed the losses in pre-stress due to relaxation of steel, and we have discussed the effect of creep and shrinkage in the losses with an example problem, and we also explained the IS 1343 code provisions for estimation of the losses and how to use the equations and what are the different, you can use the table values or you can use the equations. Usually when you use the equations, you tend to get more accurate and less conservative estimation of your losses. So with that, we are completing the module 2. Thank you for your attention. Happy learning.